So when you're trying to calculate the molar mass of a covalently bonded compound, we call that as the molecular mass. And the way to calculate that is by adding the atomic mass for all the atoms that are part of that molecule. So, for example, if we're talking about water, in order to calculate the molecular mass for water, you'll have to add the atomic mass of hydrogen twice, because again, we have two atoms of hydrogen as well as a single atom of oxygen. So adding the atomic mass of oxygen plus 2 times the atomic mass for hydrogen would would result in the molecular mass for the water molecule for the H2O. Now, the reason why we call it molecular mass, as I said earlier, because we're talking about covalent compounds. Um, but in general, the molar mass or the molecular mass in this case, because we're talking about the water molecule, which is a covalent bond molecule, it basically means the sum of all the atomic masses of the atoms of that specific molecule. So the sum of the atomic masses of the atoms in that molecule, as you see the definition right here. So that's when we're talking about covalent compounds. On the other hand, when we're talking about ionic compounds, it's the same concept, which is adding the atomic masses of all atoms that are part of that molecule. However, we call it a different name in this case, and we call it the formula mass. So if you're talking about ionic compound, instead of calling it a molar mass, we call it a formula mass. If we're talking about a covalent compound, we call that as a molecular mass. Okay? The concept is pretty much the same, which is the summation of all atomic masses of the atoms that are part of that compound. So, if you're talking about something like NaCl, for example, in order to find out what is the formula mass for the sodium chloride, what you do is you add the atomic mass for the sodium for the periodic table and the atomic mass for the chlorine. Add them both together, that would be equal to 58.4425 gram per mole. The molar mass for sodium chloride, or the formula mass for the NaCl. As I said earlier, it's pretty much the same concept, which is the sum of all the atomic masses of the atoms that are part of that formula. It's called differently. Okay? So let's try an example. So a typical glass of wine contains about 16 grams of ethanol. The formula for the ethanol is C2H5OH. First, what we need to find out the molecular mass for the ethanol. Why do we call it a molecular mass, not a formula mass? Because every element or every atom we have here is for a nonmetal. So we're talking about covalent compounds. As a result, we call it a molecular mass. Okay? And then once we find out the molecular mass for that, we would like to calculate the mass of 1 mole of the C2H5OH, or the ethanol. And then we will do the conversion, and then we will do how many moles of ethanol are 16 grams of C2H5. Okay? So what we need to do first, we need to find out what is the molecular mass for the C2H5OH. Okay, so in order to calculate the molecular mass for the C2H5OH, we need to find out what are the atomic masses for the carbon, for the hydrogen, for the oxygen, and that's pretty much all. So what we need to do is we need to find out the atomic mass for the carbon, the atomic mass for the hydrogen, and same thing for the oxygen. All that can be obtained from the periodic table. So when you look at the carbon, for example, the atomic mass for the carbon is 12.01 gram per mole. For the hydrogen, it is 1.007 gram per mole. And for the oxygen, it is about 16 gram per mole. Okay, so now that we know all the atomic masses for the carbon, for the hydrogen, as well as the oxygen, what we need to do is we need just to basically add them all up together to calculate the molecular mass for the ethanol. What we need to consider, however, all these subscripts down here, because these will multiply by the corresponding atomic mass for that element. Well, what does that mean? So, for example, if I'm doing for the carbon, in order to calculate the atomic mass for the carbon, oops, sorry about that, the atomic mass for the carbon within the ethanol, what I need to do is I need to multiply that by 2. So it's going to be 2 times 12.01 gram per mole. And then for the hydrogen, I will have to multiply the atomic mass for hydrogen by a factor of 5 because of the subscript that I have here, that is 5. So that's going to be 5 times 1.007. For the oxygen, since I have only one oxygen, so that would be 16. Plus, for the hydrogen, I still have one more hydrogen, 1.007. So what some people, what you might see also some people doing, instead of writing another hydrogen at the end, what they do is they multiply. Okay, so there's too much delete. They will make this as a 6 because you have 5 in here and have another hydrogen in here. So you multiply the atomic mass of hydrogen by a factor of 6. Now, once you add all these up together using your calculator, the number or the atomic or the molecular mass for the ethanol would be 46.07 gram per mole. I can either write it this way or I can also write it this way. I can say gram per mole. Okay? So when we say on the next question, so this is how you calculate the molecular mass for the ethanol. Another way to address that question, I might ask, what is the mass of 1 mole of ethanol? Because again, when we say 46.07 per 1 mole, so that would be another way to ask you to calculate the molecular mass for the ethanol. Or I can also ask to write a conversion factor between mass and moles. And every time you see these words together associated with convert between, that means you'll have to calculate the molecular mass for that compound, okay? Because as you see here, the only way to relate the grams and the moles of a chemical compound is by calculating their molecular mass, okay? So that would be another way to calculate the molecular mass, either by asking you the mass of or the mass of a 1 mole of substance or of a chemical compound or chemical material, or to write the conversion between a mass and a mole, okay? A gram and mole. The next question here, how many moles of ethanol are in 16 grams? And again, as you see here, there is no way for us to solve this problem converting the moles, the 16 grams of ethanol into moles of ethanol is by using the conversion factor of the molecular mass, okay? Because the molecular mass will give me the tool to convert between grams and moles. So I'm going to use the molecular mass that I just calculated to convert 16 grams of ethanol to what's equivalent of moles. So I have 16 grams of ethanol, and I'm going to use my conversion factor here. Again, when you're looking at a fraction of a conversion factor, you can rearrange that all the time depending on which unit you're trying to cancel. So since I have a grams in here, I'm going to need to have my grams in my denominator so I can cancel it out later, okay? And then my final answer has to be in moles, so my nominator has to be in mole, okay? Now I'm going back to my conversion factor that I just calculated, which is every 1 mole equal to 46.07 grams. Now I'm going to cancel my grams, and I'm going to end up with moles, which is my unit at the end. Now, once you do that in the calculator, you divide 16 by 46.07. That would equal to 0.35 moles. So every 16 grams of C2H5OH equal to 0.35 mole of C2H5OH. The only way that you can convert grams 2 moles is by calculating the molecular mass. Please pay attention to this. Okay? Um, let's try to do another example here. So, water from coal mines is contaminated with sulfuric acid that forms when water react with iron sulfate. Okay? So first what we need to do is we need to write a conversion factor to convert between grams of the ionic compounds and moles of the iron sulfate. So every time when we say conversion factor between grams and mole, first thing that needs to pop into our head is calculating the molar mass. Or if you want to be more specific, because we're talking about ionic compound, we can call this a formula mass. But calling it a molar mass is acceptable with me. So that's fine too. So we need to calculate the conversion factor, or we need to figure out the conversion factor by calculating the molar mass. And then once we do that, we need to calculate how many moles are in 2.67 pounds of the Fe2SO4 of the iron sulfate. So in order for us to convert pounds to moles, we need to calculate our molar mass. So the conversion factor that we're going to calculate in the first part of this question will help us answer the second part. So first what we need to do is we need to calculate the molar mass. How do we calculate the molar mass, or the formula mass in this case? It is the summation of all atomic masses in that chemical formula. So in this case, I have iron. So if you look at iron in the periodic table, the atomic mass for iron is 55.84 gram per mole. But since I have 2 of the iron, I'll have to multiply that by 2. Right? We're talking about Fe2SO4 sulfate 3. So I have 2 of the iron. Never forget the subsecrets. Plus, I have 3 of the sulfate, so I'm going to open 3 and start with a big parentheses here. So I have the sulfur. The atomic mass for sulfur is 32.01 or 0.6, I'm sorry, 06. Sorry about that. 06. Plus, for the oxygen, I have 4 of the oxygen. So I have 4 times 16. So remember, 4 times 16, that's a 64. So 64 plus 32, and then you multiply that figure, all of it, by a factor of 3, because I have 3 of the sulfate. So I'm calculating the molar mass for the sulfate, and I'm multiplying that by a factor of 3, because this is how many sulfates I have in my ionic formula, right? I have 3 of the sulfate, not a single one. So, and then you multiply 2 by the atomic mass for the iron. Once you add all this up together, the molar mass for the iron sulfate will be 399.7 gram per mole. So this is the molar mass, or the formula mass, for the iron sulfate. And in the same time, this is the conversion factor between between grams of iron sulfate to moles of iron sulfate, and vice versa. So if I have grams of iron sulfate, I can convert that into moles. And if I have moles, I can convert that into grams using this conversion factor, just like how we are going to do in the second part. Okay? So in the second part, what I have here, I have pounds, and I'd like to convert that into moles. But before I do so, my conversion factor between between moles has to be between moles and a gram. So what I need to do before even applying my conversion factor, I'll have to convert my pounds into grams. Okay, so using my English to metric system conversion factor, convert my pounds into grams, and then I should be good to go to use my molar mass in this case. So first off, what I need to do, I need to convert my pounds, oops, 672 pounds, and I'll have to multiply that so I can convert it into grams. So what I need to have grams in my numerator and pounds in my denominator. Okay? Clean this up. And we know for every 1 pound, there's 453.59 grams. Okay? So once, at this point, now I have converted my pounds into grams, right? Because what I can do, essentially, I can cancel out the pounds with the pounds, and now I'm left off with the grams. Now it's time for me to use my molar mass conversion factor. So I have grams down here, and I have mole up here. Why do I need the mole? Because at the end of the day, I need to have mole as my unit. I'm converting from grams to moles. Okay? Now, again, I'm flipping my conversion factor here, right? Because I need to cancel out the grams. So you need to make sure that you do that correspondingly. So what you need to do is you will have to put the 399.7 in your denominator, and the 1 moles will be in your denominator. Okay? So now I can cancel the gram with a gram, and I am left with a mole. So what I need to do is I need to multiply 2.672 times 443, which is the grams in a pound, and then I'll have to divide that by the factor of 399.7, which is my molar mass for the iron sulfate. Once you do all this, the number of moles is 303 mole. So there is about 3 moles in 2.672 of the iron sulfate compound. Okay, so let's summarize everything for the molar mass. First, before we got into talking about the molecular mass and the formula mass, we talked about the atomic mass, which is the number that we get from the periodic table. Okay, so the molar mass of the element, it's basically the atomic mass in grams of that atom in grams. So we're talking about carbon, hydrogen, oxygen. The number that we get from the periodic table, which represents the mass of the nucleus between the protons and neutrons, that would be the atomic mass of that element. Okay? When it comes to the molar mass, on the other hand, the molar mass for a molecular compound or covalent compounds, it's basically the summation of all atomic masses of all the elements in that chemical formula. We uh, calculate the same thing for ionic compound, and we call that as a formula mass, but it's essentially the same concept, which is adding all the atomic masses of all the elements that are part of that chemical formula. The thing that you need to always consider and keep in mind is the subscript that you have in the chemical formula. So, like when we are calculating for the ethanol, the C2H5OH, or even for the sulfate for the iron, the subscript of 2, you need to always pay attention to this and multiply your atomic mass by the corresponding subscript that you have in that chemical formula. Okay, otherwise your molar mass formula or molecular mass will be incorrect. So sometimes when it comes to moles to moles conversions, the subscript that we have within the molecular formula actually helps us convert between units of the single atom, which is the part, to the units of the whole of the chemical formula itself. Okay, well, how does that work? That basically works out, and we can use that as the moles to moles conversion. So, a compound formula provides us with a conversion factor that converts from units of a part to the units of a whole. So when you're looking at something like the phosphorus oxide, which is the P4O10, the 4 for the phosphorus and the 10 for the oxygen, it helps us convert between the part, which is for example, the units for the phosphorus, to the unit of the phosphorus oxide as the chemical formula, as a whole chemical formula. So when I look at this one, when I look at the phosphorus oxide, what I can say, because I have the subscript of 4 for the phosphorus, that means there are 4 atoms of phosphorus in every single molecule of phosphorus oxide, right? And I think that's kind of pretty obvious because I have 4 phosphorus within the whole molecule of the phosphorus oxide. So that is the relation between the part, and this one is the whole unit for the formula. Okay? I can take use of this concept and assume also that there are 4 moles of phosphorus within 1 mole of phosphorus oxide. So there is the part and there is the whole. So in other words, if I start with an X amount of phosphorus, I can kind of project how much of the end product I will have based on the relation of phosphorus within the phosphorus oxide, okay, based on the subscript that I have here. So that essentially serves the purpose of converting between moles to moles within the same chemical formula. Let's look at a couple more examples. So, for instance, if you're looking at the hexane, which is the C6H14, I can also, because I have the subscript here of 6, I can say there is 6 moles of carbon within one single mole of the hexane. I can also say there is 14 moles of hydrogen within a single mole of hexane. So I can basically convert between a mole of hexane into a mole of hydrogen. So if I were to ask you to convert between, for instance, 10 moles of hexane, and I want to know how many moles of hydrogen I will have, I use this relation between the hydrogen and the hexane to convert between either one of them. Okay? So that's when it comes to molecular compounds. For ionic compounds, it's pretty much the same concept. I have calcium in the calcium nitrate. So there is one calcium in the calcium nitrate. There is one unit of the calcium in the calcium nitrate as a whole. So I can say there is 1 mole of calcium in 1 mole of calcium nitrate. For the nitrogen, on the other hand, I'll have to multiply it by a factor of 2. So there's 2 moles of nitrogen within 2 moles of calcium nitrate. For the oxygen, it's a little bit more tricky because I'll have to multiply that by a factor of 3. So 2 times 3, that makes it 6 moles of oxygen within 1 mole of calcium nitrate. Okay? You can also do as a single as this is pretty much the same, but for this one you can also do the nitrate as a whole. So that is 2 moles of nitrate within the 1 mole of calcium nitrate. Okay, let's do an example. So consider a molecular compound of the phosphorus oxide, tetraphosphorus decaoxide, and the ionic compound of iron sulfate, the Fa2SO4. So first what we need to do is we need to write a conversion factor that converts between moles of phosphorus and moles of phosphorus oxide, or tetraphosphorus decaoxide. And then we'll have to find also a conversion formula between moles of iron and moles of iron sulfate. Okay? So first, writing a conversion factor between moles of phosphorus and mole of phosphorus oxide, I will have to look at the subscript of the phosphorus within the phosphorus oxide. So I have 4 units of the phosphorus within the phosphorus oxide. So what I can say, that is 4 mole phosphorus, 1 mole phosphorus oxide. Or I can also say 1 mole phosphorus oxide, 4 mole of phosphorus. I can basically rearrange my fraction depending on the unit that I'm trying to convert from and convert to. Okay? The second part here is write a conversion factor that converts between moles of iron and moles of iron sulfate. And again, the formula that I have for the iron sulfate is Fa2SO4, and I have 3 of the sulfate. So every 2 moles of iron exist in 1 mole of iron sulfate. This is 1 mole. Or I can rearrange this and it would still be correct. I can say 1 mole of Fe2SO4, SO4 contains 2, nope, not 4, these 2 mole of Fe2 plus ions. I can take this even a step beyond that, and if I want to calculate the moles or create a relation, the conversion factor between sulfate and the iron sulfate, I can say 3 mole of the sulfate, 2 negative, exist in 1 mole within the iron sulfate. Again, because this subscript here does not only represent the number of moles, it represents the number of units. So we can say atoms, we can say grams, we can say kilograms, we can say pounds, but in this case we're converting between moles to moles. Okay, so out of 3 mole of the sulfate exists in 1 mole of the iron sulfate. Okay, so how many moles of the sulfates are in 1 mole of the iron sulfate? That's pretty much answers down here. And again, you can always flip your fraction down here, depending on the unit that you're trying to convert to. Okay? So that's the mole to mole conversion. Let's put everything together. So what is the maximum of the phosphorus oxide that can be formed from 1.09 times 10 to the power 4 kg of the phosphorus? So we have 1.09 times 10 to the power 4 kilograms of phosphorus. And we would like to know how much we will be getting, or how much we'll be getting of the phosphorus oxide if we know how much we're starting with the phosphorus. Okay, so now we are going to take advantage of the relationship of the phosphorus within the phosphorus oxide. And we know there is 4 moles of phosphorus within the phosphorus oxide. Okay? But because we're talking about moles, we are starting with kilograms of phosphorus. And we can convert mole to mole. Okay? But in order to make this number applicable to our mole to mole conversion, what we need to do is we need to convert the kg of phosphorus into moles of phosphorus. Okay? P4O10. And then once I convert my kilograms into moles of phosphorus, then I can apply my mole to mole relation conversion factor. Then I can calculate how many moles of the phosphorus oxide that I have or I can get. Okay? Once I calculate how many moles of the phosphorus oxide, then I can convert that into grams or kilograms. Okay? So what I'm starting here, I'm starting with 1.009 times 10 to the power 4 kg of the phosphorus. First, what I will do is I'm going to convert the kg into grams. Okay? So I can cancel out the kg with the kg. Well, someone will say, well, why are we converting the kilograms to grams? Why not use the kilograms, as is? Well, we can't because we would like to convert the grams or the kg into mole. And we know the only way that we can convert to mole is by the relation of gram to mole, which is equal to the atomic mass from the periodic table. So the atomic mass for the phosphorus from the periodic table is 30.97 gram per mole. In order for me to use this conversion factor or this atomic mass, I need to convert my kilograms into grams first, right? Because that's the unit that I have for gram per mole for the atomic mass. That is the reason why I am converting kilograms into grams, okay? So first what I'm doing is, again, converting kilograms into grams. So kg now converts to grams, so the kg can cancel out. Now I can use my atomic mass, which is from the periodic table. Periodic table. I can cancel out grams with the grams. So guess what? Now my kilograms now is actually converted or has been converted into moles. Now I can use my mole to mole relation from the formula of the P4O10 that in every single mole of the phosphorus oxide that is 4 mole of phosphorus. Okay? So now mole can cancel out with a mole. So up to this point here, I have mole tetraphosphorus pentaoxide. But now what I need to do is, my question is about the maximum mass of the tetraphosphorus decaoxide. What I need to do now, I need to convert the mole into gram. Well, how do I convert between moles to gram? Answer, molar mass. I need to calculate the molar mass for the phosphorus oxide or tetraphosphorus pentaoxide. How do we calculate the molar mass for P4O10? That would be the atomic mass for phosphorus times 4, atomic mass for oxygen times 10. So that would be 4 times 30.97 gram per mole. This is from the periodic table. Plus 10 times 16 gram per mole for the oxygen. And this will be from the periodic table as well. You add all these up together, that would be 284 grams per mole of phosphorus oxide. Now I can convert my moles of phosphorus oxide into grams because now the mole can cancel out with the mole. Okay? Up to this point, I have a gram P4O10. But this is yet just not enough because I need to convert the grams of P4O10 into kg. Remember, we started with the kg. And that should be an easy step because what we can do is we can just divide that by 1,000 as you see here, cancel out the grams, and then you will end up with the kg, okay? And that would be about 24.9 kg, kilograms of phosphorus oxide, okay? After multiplying all these numbers on your calculator. So that's how we can use and take advantage of the subscripts that we have here that represents the number of the units within the whole chemical compound or the chemical formula to convert between moles to moles, so we can figure out exactly how much we will have in a chemical reaction similar to this if we know how much exactly we have of one of the parts of that whole chemical formula. Okay? So let's summarize everything when it comes to converting between moles to moles. First, you can start with any unit of the element. Okay, So, and then we can convert that. So if we started with a kg, for example, just like how we did at the early example, we have to convert that into grams. If we started with a pound, we have to convert that into grams. So your first universal step is you need to convert to gram regardless. So if you're not sure exactly how to execute this kind of problems, I can give you a quick tip. Just convert that to grams. Convert the first unit that you have into grams, and that at least you can get, a partial credit if you start, just in case you make mistakes later. But the universal step in any conversion between part to whole, or converting moles to moles, you'll have to convert into grams. So you have to start with the unit of gram all the time. Then you'll have to convert the grams into moles. And this can happen by calculating the molar mass. Okay? And the molar mass is obtained from adding up all the atomic masses of that elements within that chemical formula. Okay? Then once you calculate the number of moles, then you're set to go to use the mole to mole conversion. Okay? So in this case, the P4O10, then you can use the 4 mole phosphorus in every 1 mole, I'm sorry, the 4 mole phosphorus in 1 mole of phosphorus oxide. Mole. Forgetting my mole here. 1 mole. So once you have converted the unit that you started with down to moles of phosphorus, then at this point you can use your the mole ratio from the compound formula. Then you calculated the moles of the compound containing that element. Then you can, using the molar mass derived formula, again by calculating the molar mass, adding up all the atomic masses from the periodic table, you will convert this mole into grams. Okay, and then at the end you will convert your grams to any unit that you desire based on the question that you've been asked to do. Okay, so that's basically a general run through for the whole steps of converting from grams, or starting with any unit, converting to grams, and then converting the grams into moles using the molar mass, atomic mass of the periodic table, then converting the moles into the mole of the other compound that you're trying to calculate using the mole ratio of the compound that you have, and then converting the moles into grams, and then the grams to the unit that you'd like to convert to. So when it comes to empirical formulas, sometimes when we write the chemical formula for a substance, we can either use the molecular formula or we would use the empirical formula. For the most part, up to this point, what we have been using when it comes to writing the chemical formula, we've been using the molecular formula, okay, which represents exactly how many atoms of that specific element within that chemical formula. Now we are going to look at something a little bit different, which is the empirical formula. And what the empirical formula means, it is when the subscript in the chemical formula represents the simplest ratio of the kinds of atoms in that compound. Okay, so the empirical formula, it's a representation of the simplest ratio of these atoms within, for that chemical compound, for that specific chemical compound. Okay, so it is the simplest ratio, not the actual representation of every count of every atom within that chemical formula. Okay, so most ionic compounds are described with their empirical formulas. That's something to keep in mind. Molecular formula, on the other hand, like I mentioned earlier, it describes the actual number of atoms of each element in that molecule. So when you're talking about something like H2O, for example, so H2O, the chemical formula H2O, that means we have 2 hydrogens and we have 1 oxygen. So it actually represents the actual count of atoms for hydrogen as well as oxygen within the chemical formula for water. Okay? Sometimes the chemical formula and the molecular formula can be the same. Okay? Well, how does that happen? So first, when you're looking at something like hydrogen peroxide, for example, the hydrogen peroxide molecular formula is H2O2, and that represents the actual count of atoms of hydrogen and oxygen. So I have two hydrogens and I have two oxygens. To convert between the molecular formula to the empirical formula, you'll have to ask yourself a simple question. Can I simplify that formula into something that it's simpler to represent the count of atoms for that chemical formula? The answer for this case for the hydrogen peroxide is yes, because I have two hydrogens and I have two oxygens. So basically, if I divide both subscript by a factor of 2, I will end up with HO as the empirical formula. So in this case, for hydrogen peroxide, the molecular formula is H2O2, and the empirical formula is HO because the HO is the simplest ratio that represents the count of atoms for hydrogen and oxygen. The molecular formula, it is not the simplest. It presents to us the actual count for hydrogen and oxygen. Same thing when you're looking at something like glucose. Some books, when they are talking about the molecular formula for glucose, they will have it as C6H12O6, which means 6 carbons, 12 hydrogen atoms, and 6 oxygens. Okay? So the molecular formula is serving the purpose of really telling us how many of each element I have within that chemical formula. Okay? Now, can I simplify this molecular formula a simplest into a simple ratio of carbon versus hydrogen versus oxygen? The answer is yes, because if I divide the carbon by 6, a factor of 6, and hydrogen by a factor of 6, and oxygen also by a factor of 6, which is basically the common denominator between 6 and 12, I will end up with CH2O. Okay? So if you are able to answer to the question of can I simplify this molecular formula as yes, then the empirical formula and the molecular formula are not the same. If you cannot simplify it into a more into a simpler version of for the formula, then the empirical formula and the molecular formula are the same. Okay. Okay. So which of these compounds, for example, represents both the molecular formula and the empirical formula at the same time? So if you look at the N2O4, for example, and you have the arrangements of oxygen, and you have nitrogen in the middle, the nitrogen both bonded to each other, and you have oxygen on the other side. Can I simplify the N2O4 into a more simple way of presenting the count of nitrogen and oxygen for that chemical formula? The answer is yes, because I can divide both by 2 and I will have NO2. So this is the molecular formula, and this one is the empirical formula because this is the simplest ratio that represents the count of nitrogen and oxygen. And as a matter of fact, if you can imagine a line that goes right in the center of nitrogen between both nitrogen. Now, this is obviously chemically not possible or it's not going to happen. But to explain exactly what a molecular formula is, if I draw a single line between both nitrogen, what I will end up with basically a symmetrical nitrogen oxygen on this side and another nitrogen and oxygen on this side with the same count of nitrogen and oxygen. So that's another indication that this can be simplified. Okay. On the other hand, when you look at the H2O4, the sulfuric acid, the question, well, can I simplify the H2SO4 into a simple ratio, into a more simple ratio than the H2SO4? The answer is no, because even if you try to divide it by 2, that means you'll have half sulfur, and that's not possible. We don't have atoms are not divided into fractions. Okay. So this one, the empirical formula and the molecular formula is the same because I cannot simplify this into a further ratio for the count of hydrogen, sulfur, and oxygen. The other thing that if you may notice here, unlike with the nitrogen and oxygen here, where I was able to draw a an imaginary line in the center where I would have a symmetrical count of nitrogen and oxygens on both sides. This is not possible in this case because even if I draw it this way, that means I'm gonna split the sulfur atom into two halves, and that's not possible. Same thing if you do it this way. Okay, so that's another indication that the empirical formula and the molecular formula is the same. Okay, likewise with this molecule, and same thing here with the vinyl chloride. Same thing with this one is, in fact, the molecular formula and the chemical formula are different because I can simplify this into a simpler ratio to represent the count of hydrogen and chlorine, right? So if I divide everything by 2, that means I'll have CHCl. So this is the empirical formula, and this is the molecular formula. So the molecular formula in this case, it really tells me how many carbon, hydrogen, and chlorine, in fact, for this chemical compound, okay? This one only represents the identity of these atoms within that chemical compound. And again, this is similar to the NO2 or the N2O4. I can actually draw a center line in the middle, an imaginary line, and I would still have the same H carbon, hydrogen carbon, and chlorine on both sides. So sometimes we can determine the empirical formula for an unknown chemical compound experimentally through the study of the decomposition product. So if you basically decompose and any chemical compound either through pyrolysis or heat or through running electric current or reacting with any other chemical reagent, the breakdown of products we can use to kind of piece back together and try to find out what is the original compound would look like, which is basically expecting or projecting what is the empirical formula. The decomposition product generally would represent the ratio of every single element that was originally part of the parent compound. Okay, so how can we calculate this? First, you need to follow the steps that I'm going to outline shortly. First, for example, if you're looking for something like this kind of data, so a product that contained carbon, hydrogen, and nitrogen, it was decomposed into a 38.67% carbon, 16.22% of hydrogen, and another 45.11 nitrogen. Okay, so we would need to use these ratios and try to figure out exactly what is the empirical formula of the parent compound that resulted with this ratios of carbon, hydrogen, and nitrogen. Basically calculating this and kind of like putting the piece of puzzle back together to find out exactly what is the empirical formula would look like. First thing first, what you need to do once you see ratios, you need to assume that you're dealing with 100 grams worth of material. That way you can convert your percentages into an actual number of grams, okay? Because once you assume you're dealing with 100 grams, that means that 38.67 would be basically a 38.67 gram, okay? Because again, when we say 38.67%, that means it's 38.67 grams per 100 grams. Remember this? Okay, that's how we convert the ratio. Same thing with 16.22%. 16.22%, if I were to assume that I'm working with 100 grams worth of a product at the end, that means the 1622 would equal to 1622 grams of hydrogen. Same deal with nitrogen. Now I have 45.11 grams of nitrogen. So now I have converted all my percentages into an actual gram, into an actual weight that I can actually use in my conversions between grams into moles, because percentages, it's basically a useless number. I can't really use it to do any conversions and figure out the ratios. So once you convert that into grams, next thing you'll have to convert that into moles. So first, I converted the percentages into gram. Now I need to convert the grams into moles. Well, how do I do this? The periodic table. Because when you're talking about carbon, hydrogen, and nitrogen, The only way that I can convert a gram into mole is through the periodic table and using the atomic mass of each element, because the atomic mass give me gram per mole conversion. So I can use this one to convert all my grams for every single element into moles. Okay, so that's almost 50% there to figure out exactly what is the ratio of each element. So step number 2, we are going to convert all the grams into moles. We have 12, the atomic mass for hydrogen, 12.01, 1.01 for the hydrogen, and 14.01 for the nitrogen. Again, this is not a negative sign, by the way. This is just a dash. So I have 38.67 grams of carbon, which is coming from my percentage of carbon within that 100%. Okay? Or 100 grams, I should say. So 38.67. Now, from the periodic table, this is from the periodic table, every 12 grams of carbon equal to 1 mole. Because remember, the atomic mass, as I said earlier, for the elements from the periodic table is a gram per mole. It is 12.01. That's how would you write it generally. But because we are converting from grams, what we will do, we will flip our fraction. So instead of saying 12.01 gram per mole, what we will say 1 mole of carbon equal to 12.01 grams. So I have flipped my fraction. So my numerator is now my denominator and vice versa. Now I can cancel my grams of carbon. Okay? And I am ending up with 3.22 moles of carbon. Same kind of process with hydrogen. For hydrogen, I have 1 mole of hydrogen equal to 1.01. Same concept as I did here. When we look up the atomic mass, it's a gram per mole, not mole per gram, but we invert our fraction so we can cancel out our grams of hydrogen. Now I have 16.09 moles of hydrogen. Okay? Same thing with nitrogen. I have 3.219 moles of nitrogen. Once you have converted the percentages into an actual grams, converted the grams into moles, what you need to do, you'll have to divide by the smallest number of moles among all your conversions that you just did. So in this case, I have 3.22, I have 16.09, and I have 3.219. So this is right here. This is the smallest. Oops. This is the smallest mole calculated for the nitrogen. So you'll divide everything by the 3.219. So you'll divide the moles of carbon, which is 3.22, by 3.219. And that would equal approximately 1. Okay? You'll divide the same thing for the hydrogen. So 16.09, that's divided by 3.219, and that would be equal to 5. For nitrogen, would be equal to 1 because we're dividing the 3.219 by 3.219. Once you have reached this step, this number basically will represent the ratio for the carbon, the ratio for the hydrogen, and the ratio for the nitrogen. Then you can write your empirical formula. So this is the empirical formula. The subscripts that you see here, these are from dividing the mole, the smallest mole calculated for one of those elements, divided by all the moles calculated for the other elements. So that would be CH5N. And these are the ratios for the empirical formula. So this is how we calculate the empirical formula, by converting grams into moles, dividing by moles, and then you will get the ratios for every element. Now, sometimes you might end up with the fractions, just like with this molecule here. What you need to do is you need to multiply each subscript by a whole number. So in this case, you'll just have to multiply by 2 because we can't have fractions. So where would this fraction be coming from? you may be dividing by the smallest number, and then you may end up with, for example, 1.5. We can't have a fraction in our empirical formula. So what we do is we divide by an integer, so we can have you divide by a whole number, so you can have an integer at the end. So for this case, 3.5, you divide everything by 2, you will have N2Cr2O7. Okay, I guess the point here that if you do the mole calculation and you end up with a fraction, please do not use the fraction here. You'll have to multiply by the denominator of that fraction to get an integer number. Okay. All right, let's summarize everything one more time. How to calculate empirical formula from experimental data. First, if you're not given a mass, so if I didn't give you the mass exactly, I'm giving you ratios, you'll have to convert the ratio into grams by assuming that you have 100 grams, okay? And then once you convert that into grams, you'll have to convert the grams of each element to moles by dividing by the atomic mass of the element from the periodic table. And then you divide each mole value by the smallest and round your answers to a whole number or common mix of fractions. Okay, and if it's not an integer, you'll have to multiply by a whole number until the ratios are integers. Okay. If you have a fraction after the last step, then you multiply all the values by the denominator of the fraction, as I said earlier, so you can have an integer number. The resulting mole values correspond to the subscripts in the empirical formula, i.e. the ratio, the simplest ratio for every element within that chemical formula. Let's do one more example. So during a drunk driving arrest, police found a white powder substance on John, and they thought initially it was cocaine. It was powdered cocaine. They took that material to the lab, and after doing some analysis, they found out there's 49% of that material was carbon, and 5.19% hydrogen, and 28.85 nitrogen, and there was 16.48% of oxygen. Okay, so you're in the lab and you did all this test, and they ask you, can you please confirm the identity of this material? Is it a narcotic substance? Is it a cocaine, or it is not? So we're going to do this, and we know the empirical formula for cocaine is C17H2NO4. So what we need to do is, based on the decomposition of the material that was found on John while he was driving, the 49% of carbon, the 5.19 for hydrogen, 28.85 for nitrogen, and 16.48 for oxygen. Based on these ratios, we'll have to figure out what is the empirical formula for this unknown substance and basically compare to the known empirical formula for cocaine. And if it is the same, then it's a positive test. If it's not the same, then he must have some powdered sugar on him for some reason. Okay. So first thing, what I need to do is I need to assume that I am working with 100-gram sample. Well, that would make the 49.48% of carbon equal to 49.48 grams carbon. Okay, so we are assuming that we're dealing with 100-gram sample. That's for the carbon. For the hydrogen, that's 5.19% hydrogen. That means it's 5.1 gram of hydrogen. For the nitrogen, the 28.85%, that would equal to 28.85 grams of nitrogen. For the oxygen, the 16.48%, that would equal to 16.48 grams of oxygen. So now I have the mass of every single element that is found as part of the decomposition of that unknown chemical compound. That's step number one. I've converted the percentages into grams. Step number two, I'll have to convert all the grams into mole. And that would be from the periodic table by obtaining the atomic masses for every element. Okay, so let's do this together. So first, I'm doing for the carbon. So for the carbon, the 49. Oh, let's do another color just for the fun of it. Okay, I'm going to do green. So 49.48 grams of carbon. I'm going to have moles in my denominator and gram carbon in my denominator. And if you look at the periodic table, every 1 mole of carbon equals to 12.01 grams in mass. Okay, so now grams can cancel out with a gram, and then it'll divide the 49.48 divided by the 12.01, and that would equal to 4.12 mole of carbon. Put that in a box. I'm going to do the same thing for the hydrogen. So the 5.19 gram of hydrogen, I'm going to multiply that by the atomic mass from the periodic table. I need moles of hydrogen. And I have grams down here. And if you look at the periodic table, it's 1.01. Cancel out. And the moles of hydrogen is 5.13 mole hydrogen. Let's do the nitrogen now. For the nitrogen, I have 28.85 grams of nitrogen. Multiply that by the atomic mass for the nitrogen, which is 1 mole. Nitrogen has a mass of 14 grams in mass. Okay? Gram cancel out with a gram. And then my number of moles of nitrogen is going to be 2.06 mole of nitrogen. I'm going to put this one in a box. Okay? Lastly, the oxygen. I have 16.48 grams of oxygen. I'm going to multiply that by the atomic mass for oxygen, which is 1 mole of oxygen, equals to 16 grams. Cancel out grams, and that would equal to 1.03 mole oxygen. So now I have converted all my grams for all the elements that are part of that unknown formula into moles. Okay? Now I'll have to find out which one is the smallest mole calculated for one of those elements. And it's pretty obvious, is the oxygen. So the oxygen has the smallest number of moles as part of that formula. Now I'm going to divide all the moles that I've calculated for every single element of those by the factor of 1.03, okay? In order to find out exactly what is the ratio for every element in that chemical formula. So that would be, so for the carbon and for the hydrogen and for the nitrogen and for the oxygen. So for the carbon, that would be the 4.12 divided by 1.03. For the hydrogen, that would be the 5.13 divided by the 1.03. For the nitrogen, that would be the 2.06 divided by 1.03. For the oxygen would be the 1.03 and it's divided by the 1.03. The results of these fractions, this would basically represent the ratio for every atom, for every element in that empirical formula. So if you divide the 4.12 divided by the 1.03, that would equal to 4. For the hydrogen, that would be a 5. For the nitrogen, that would be a 2. For the oxygen, that's a 1. So this is the empirical formula for that unknown material determined experimentally, okay? Now, if I compare this one to the formula of cocaine, it's C17H2NO4. It's not even close to the chemical structure of cocaine. So he basically did not have any narcotic on him when he was driving. So it must be just kind of maybe starch or something else. Okay. So this is how we calculated the empirical formula. This is how we figured out the empirical formula experimentally through the decomposition products of that chemical compound. Okay. So this is basically a summary of everything that I just talked about. Okay. I think we explained it a couple of times, so I'm not gonna repeat that one. Sometimes we can convert the empirical formula to a molecular formula. Okay. How can this happen? By using the molecular mass, and you divide that by the empirical formula mass. Okay, because remember, when we are talking about the empirical formula in this case for the cocaine, this empirical formula mass in this case, um, or actually a better example, if we are talking about, let's go back here. So where is the hydrogen peroxide? So when we are talking about the hydrogen peroxide, delete this one. So the molecular formula, this one right here, will have a different mass than the empirical formula. Don't you agree? Because with the molecular formula, you have two hydrogens and you have two oxygens. Okay? With the empirical formula, you have one hydrogen and you have one oxygen. So essentially, in this case, you have 17 or somewhere around 17 grams per mole. In this case here, you have 32 plus 2, so that's about 34 grams per mole. So the empirical formula mass is different than the molecular formula mass. And that's kind of evident because with the molecular formula, we're giving the exact count of atoms in that chemical formula. So the molecular formula mass will be higher compared to the empirical formula. So between these two calculations, the empirical formula mass and the molecular formula mass, we can actually figure out the molecular formula from the empirical formula, okay? By dividing the molecular mass divided by the empirical formula mass. You'll get a number, we call that a N, and you multiply our empirical formula by this factor. Let's do an example, okay? So, an experiment shows that adipic acid is 49.31% of carbon, 6.9% hydrogen, 43.79% of oxygen, which converts to an empirical formula of C3H5O2. So the empirical formula has already been given. So we are skipping the part of doing the percentages to grams. We're skipping the part of grams to moles, dividing by moles, all these kind of steps we're skipping because we have the empirical formula right here. From a separate experiment, the molecular mass of adipic acid is found to be 146.144 grams per mole. What is the molecular formula for adipic acid? So we have the empirical formula, we have the molecular mass, and we need to find out what is the molecular formula, okay? So we are going to use this equation that we just talked about a second ago. All right, let's put it into business. So this is the empirical formula. This is the empirical formula. In order to really figure out what is the molecular formula, we need to calculate the number n, which is the molecular mass divided by the empirical formulas. The molecular mass has already been given, which is the 146.144 gram per mole. I believe that's, yep, 146.144 grams per mole. The empirical formula mass, however, needs to be calculated. Well, how do I calculate that one? I have 3 of the carbon, 5 of the hydrogen, 2 of the oxygen. So I need to add all these atomic masses all together so I can calculate my empirical formula mass. So the empirical formula mass would equal to 3, which is the subscript for carbon, multiplied by the atomic mass for carbon. And then 5 divided by the atomic mass for hydrogen, and then 2 divided by 15.99, which is the atomic mass for oxygen. You add all these numbers together, this is the empirical formula mass. So now I have the molecular formula, which has already been given as part of the question, and you've calculated the empirical formula, which is the 73.07. You divide the 146 divided by the 73. This number here that you get, the 2, the one that we just calculated, you multiply that by all the subscripts for all the elements in the empirical formula. Okay? So C3 times 2, H5 times 2, and O2 times 2, which would give us C6, H10, O4. And that is the molecular formula. So using the empirical formula that I have here, using the mass of the empirical formula, and by knowing what is the molecular mass for that compound, you divide the molecular mass by the empirical formula mass. You'll get a number that it's a fact that's is defined as an n, and you multiply all the subscripts by that factor, so you are able to obtain the molecular formula for that unknown material. Okay. So I think with this one, this concludes Unit 8. For calculations, please try to submit your homework, and I might even think of submitting or making some practice problems more available for these conversions. And of course, we'll continue to do some practice and give you some practice in the lab as well as a credit to your lab report. And hopefully you're able to get the hang of this. Okay?